We'll cover the next part of light, which is about refraction of light. We will study about the bending of light. We will also study about refractive index of light. Okay, so we can see these are the things that we will cover. We will know about the terms used in refraction, which is normal, angle of incidence, angle of refraction. You also apply the relationship sine I over sine R equals to refractive index, and also explain refractive index in terms of the ratio of speed of light in vacuum to the speed of light in the medium. Okay, we'll start off with a few examples that are caused by refractions. Okay, the first one is rainbow. You can read yourself in the textbook. Okay, and the formation of a mirage. All these are examples of refraction of light naturally in the air. Okay, and then these are also some. So these are also some examples of refraction. You can see that for half submerged object like the pencil and the man, okay, they appears to be distorted. It appears to be bent, like not connected to each other. Okay, but this is actually because of refraction. And then also refraction causes objects to appear nearer to the surface than it really is. So look at the swimming pool, it looks like it's very shallow, but in actual fact is deeper than it looks like. Okay, so object appears nearer to the surface because of refraction. Okay, so we move on into the definition of refraction. Okay, this can be found in a textbook. You need to know that refraction is the bending of light where it passes from one medium to another because of the change in speed of light. Okay, so you can see there's two examples over here. The white color medium and the blue color mediums are two different mediums. Okay, mediums are like your air, solid, liquid. Okay, so when I move from, let's say, the white color medium air into another medium, okay, you can see that my light wave doesn't pass through straight, my light wave will get bent. Okay, we'll talk about the bending of light waves later on. Okay, so how or why does light wave bend? You can read this in your textbook. They use examples of car. Okay, so you have a car moving on a flat solid ground. As it enters a soft sandy ground, the speed of the car will be slowed down. When it enters at an angle, okay, you will see that one side of the wheel will reach the soft sandy ground when will slow down first compared to the other wheel, which is on the flat solid ground. And this will cause the entire car to turn. The same goes for light. When light passes through from one medium where the speed is faster to another medium where the speed changes, it will also bend. Okay, and then this one you can read yourself. Okay, and this slide is about talking about light is also wave, as you have learned in EM spectrum. Visible light is part of the EM spectrum, so light is also a form of wave. So when you have light shining from one medium to another, it will bend. Okay, so this color line over here is your, use my laser pointer. So this is the light wave. Okay, and if you were to draw the wavefronts is always 90 degrees to the direction of the wave. So the wavefronts are all these lines. Okay, so when you can see that the wavefronts will also get bent. Okay, we move on into the bending of light. This was covered in Sec 2. We say that when light moves from one medium to another, the speed of light changes and the light wave bends. Okay, then how do we know how does the light wave bend? It depends on which type of medium does the light enters. Then we talk about the optical density of a medium. We need to use the word optical because this is in the chapter of light. We don't say medium. This medium is denser than the other medium. We say that this medium is optically denser than the other medium. Okay, so we have three different types of media possible. They are the solid, liquid, gas. Okay, and you can visualize in solid, the particles there's a lot of particles closely packed. Okay, the light is very hard for light to pass through it. We say that it is very optically dense. Many particles squeezed together, optically dense, and the speed of light will be slower. Okay, as compared to in gas. In gas, the particles are very far apart. We say that the optical density is very low and the speed of light is very fast. There's not much particles blocking the path of light. Okay, so we move on. You can take a look at the first example. When I have light ray moving from air to glass, air is said to be optically less dense to glass, which is optically denser. So in air, it will be faster than in glass. So we say the speed of light slows down from fast to slow. Okay, you can try for the rest. From water to air is again from optically less dense. Air is the least dense one. So it's from optically less dense to optically denser. And the speed again, speed up. Slows down, sorry, fast to slow. And then when I move from glass to air, I'm from optically denser to optically less dense. So I'll speed up. And from water to air, again, optically denser to optically less dense. And I will speed up as well, from slow to fast. Okay, and this is what you have learned in lower sec. When I move from a optically less dense to an optically denser medium, okay, like from air to glass or air to water, my speed of light will slow down. And when I slow down, I will bend towards the number. Okay, fast, slow, towards, FST. Okay, in fact, every time it slows down, it will bend towards the normal. You just have to remember that. Okay, and it's vice versa. When I speed up, I will bend away from the normal. So you can see I have light ray, this red color line. I hit interface between the air and glass. So whenever I hit the interface, the first step I need to draw my normal, which is this black dotted line. Okay, after I draw this normal, I will see that my light ray will not just pass through straight, because there's a change in the speed. The speed will slow down in glass because glass is optically denser. And same for this, it will slow down in water as well, because water is also optically denser than air. So when I slow down, I'll bend towards the normal. So instead of passing straight, I'll bend nearer towards my normal. So I will have this. Okay, and then vice versa, when I speed up, okay, so you can see from glass to air is less dense, so the speed will be faster. Whenever I speed up, I'll bend away. When I slow down, I'll bend towards. Okay, so instead of going through straight, I bend away, further away from my normal. Okay, so you may try out these few examples. The first one, from air to water, you know that water is optically denser. So denser, slow down, I'll bend towards the normal. Okay, then plastic compared with air, you should know that air is optically less dense. It will be faster. I'll bend away from the normal. Okay, so away from the orange line. Okay, next one, from air to glass. Again, I am moving from fast to slow. Glass is slower. So when glass is slower, I bend towards the normal. And from water to air is faster. I'll bend away from the normal. Okay, next, some of the important terms that you need to know, just like for reflection, they are quite similar. Okay, the first one, okay, the ray that hits the surface is called the incident ray. Okay, and then after that, when it passes through a glass block, some of it will get reflected, bounce off, okay, which is this weak reflected ray. Okay, but majority of it will pass through the transparent glass block. And when it passes through a transparent glass block, because of the change in speed, I will bend towards the normal, because I am slower in glass, so bend towards the normal. So when it bends, it's called the refracted ray over here. And then after that, when I am moving from glass out to the air, again, because of the change in medium, air will be faster, so I bend away from the normal. So you can see that the ray that comes out will be called emergent ray. Okay, so just take note that if the two sides where the light ray enters and leaves are parallel to each other, so I'm going to highlight, okay, this is the side where the light enters the medium, and this is the side where the light leaves the medium. Okay, if these two highlighted sides are parallel to each other, then the incident ray and the emergent ray will also be parallel to each other. Okay, but if in the case that they are not parallel to each other, for example, in this case, a triangle glass block, okay, if my light is entering from here, okay, so you can see that this surface, use a lighter, this surface that it enters will not be parallel to this surface that it leaves. So you don't expect the rays that leave it to be parallel to it. Okay, it will not be parallel to it. Okay, in fact, it will be bending downwards, which is the one in color, the one in blue. Okay, the blue one. Okay, they will not be parallel because the two sides where it enters and leaves, the incident ray and the emergent ray, will not be parallel because the two sides, these highlighted two sides, are not parallel to each other. Okay, next, now we look at the angles, which is more important. Okay, in upper sec, you need to learn about the angles that it bends. So later on, we'll move on to the calculation parts for the angles. Okay, so again, between the ray and normal is the angles that we are interested in. So every time the normal must be drawn. Okay, so the first one, between the incident ray and the normal. So again, the incident ray strikes the surface, you need to draw the normal at here. Okay, whenever I leave another interface, I need to draw my normal again. So this is called the incident, angle of incidence. And then between the refracted ray and the normal, which is over here, okay, it's called the angle of refraction. Okay, if you were to use your mathematics, you should know that the alternate angles, okay, alternate angles, this angle over here will also be angle of refraction. Okay, the Z alternate angles, same angle. Okay, and then the angle between the ray and the emergent ray and the normal will be called the angle of emergence. Okay, so you may pause the video for a short time to work out the angle of incidence and angle of refraction in each case. Okay, so for the first example, it's very straightforward. Okay, between the ray and the normal will be the angles that I'm interested in. So this is the incident ray, so this will be the angle of incidence, 40, and this will be the angle of refraction, the band ray. Okay, 20. Okay, next one, I am interested in the angle between the ray and the normal. So I'm interested in this angle and between the refracted ray and the normal. So I need to use 90 minus 35 to get 55 and 90 minus 60 to get 30. And then the last one, okay, the normal is not drawn for you, so I need to draw the normal first, which is my first step. Okay, so again, I'm interested between the ray and the normal. So I'm interested in this angle. So to get this angle, I take 130 minus away the 90. I get 40. And then between the refracted ray and the normal, I'm interested in this angle, which will be 110 minus 90. That will give me 20. Okay, so you may pause the video to think about this question again. At what angle of incidence in the air will light pass through another transparent medium without being refracted? Okay, so just now all the examples shows light ray entering a medium, another medium at an angle. Okay, now I'm asking you, what special angle will it be such that I can move from one medium to another and yet the light does not get refracted, does not get bent? The answer is when the angle of incidence is 0. Okay, if I were to enter at an angle, okay, so what do I mean by enter at an angle? So my normal will be here. I enter at an angle, so I have an angle of incidence. When I have an angle of incidence, I will have an angle of refraction. So I enter medium X, which is said to be optically denser. So denser, I'll bend towards the normal. So I'll bend downwards like this. Okay, bend towards the normal. And this will be my angle of refraction. When I have I will have R. But in this case, the black line that you have seen, my normal is also along this black line over here. So I will say that my I is 0, R will also be 0. Okay, the light ray will actually enters, it will slow down in medium X. It will still get slowed down in medium X. But because the angle is 0, both of the wheels or both the entire light ray slows down at the same time. So the light ray doesn't get bent. Okay, it will just pass through straight. And then similarly, when it leaves the medium X, it will again speed up. But again, there will be no bending. Okay, so normal question will come out like this. When I have a light ray shining onto a semicircular glass block, okay, why at this point of time, at this region over here, let me use another color. Okay, why is it that in this region over here, why is there no bending? How come the light ray just pass through straight over here? Okay, it's again because the angle of incidence will be equals to 0. If you can see, my normal will exactly My normal will exactly be along this line. Okay, so angle of incidence is 0. Angle of refraction will also be 0. So the light ray doesn't bend when it enters from air into glass block at this point of time. Okay, next one. Which material in the diagram below is the most optically dense? Explain your answer. I hope you remember that the more dense, the more optically dense, the more I bend. Okay, the more I will bend towards the normal. So in material A and material B, I just need to observe in which material does the light ray bend more. So you can see that the light ray actually bends more in material B. So if I bend more in material B, it means that material B must be optically denser. So the light ray will slow down more and the light ray will bend more towards the normal. Okay, then we move on into the laws. Okay, the first law of refraction is the same as the law of reflection, which states that the incident ray, refracted ray, and the normal at the point of incidence all lies in the same plane. That means they're on the same surface, but this is seldom tested. Okay, we are more interested in the second law. Okay, the second law is actually also known as the Snell's law. Okay, in lower sec, you learn that the light ray bends, and you learn also that when does it bend towards the normal and when does it bend away from the normal. But for upper sec, it is slightly more. You need to know how to do the calculation for the angles that it bends. So the second law will come in. Okay, the second law says that for a medium, for two given medium, the ratio of sine I over sine R will always be a constant. And this constant is actually referring to the refractive index of a medium. Okay, I'll talk about that in depth. So we take a look at the example. Okay, I have light ray moving from air to water. We know that water is optically denser. So in water, the light ray will actually bend towards the normal because it's optically denser. So I have 3 different light rays shining at different angles. Okay, all of them, you will have your light ray bending towards the normal. So based on the second law of refraction, which is also known as the Snell's law, it says that the ratio of sine I to sine R will always be a constant. It means that, let's say I take a look at the first example over here. This is my laser pointer. First example over here. My light ray enters at an angle of I1. I gets bent at an angle of R1. So if I have this ratio, sine I1 over sine R1, if I were to sub in the values, I will get a number. This number is 1.33. It's also known as the refractive index of water. If I were to change another angle, I were to increase the angle of I1 to I2, change another angle, my light ray will again bend towards normal, but my angle of refraction will be different. R1 will be different from R2. But if I were to use sine I2 over sine R2, I will again get 1.33. The same, if I were to use sine I3 over sine R3, I will again get 1.33. Okay, so no matter what angle that I shine in at, the ratio of sine I over sine R will always be the same number. And that number always refers to the refractive index of the medium. Okay, we'll zoom in. What exactly is refractive index again? Okay, you need to know that refractive index is actually a measure of the optical density. Okay, we cannot just say, oh, light is we cannot just say that like glass is optically denser than air. But how much is it optically denser by? Okay, so we use a number to represent the optical density of different medium. And that number to represent the optical density of different medium is called the refractive index of the medium. So refractive index of a medium is defined as the ratio of the speed of light in vacuum to the speed of light in that medium. Okay, we know that in an optically denser medium, it will slow down the speed of light. So How much time does it slow down the speed of light? Is actually a measure of the optical density of the material. It simply means that the higher the optical density, the higher the refractive index, and therefore the slower the speed of light in that medium. More dense, slower speed, higher refractive index. Okay, so in formula sense, is N. N represents the refractive index. N equals to C over V, where C is always the speed of light in vacuum. You should have learned under EM spectrum, light, visible light, the speed of visible light in a vacuum, the magic number is 3 times 10 to the power 8 meters per second. Okay, this C is always speed of light in vacuum, 3 times 10 to the power 8 meters per second. It will not change. And you cannot have light traveling faster than 3 times 10 to the power 8 in any other medium. Okay, so the second one, C over V. V is the speed of light in the other medium that you're interested in. In this medium, the speed of light will definitely be less than 3 times 10 to the power 8 meters per second. It will slow down. Slow down by how much time? That will give you the refractive index of the medium. Okay, we'll give you examples later on. For now, you just memorize the formula. N equals to C over V, where C is speed of light in vacuum over speed of light in the medium. Okay, and we can also use refractive index in terms of the angle. So that is just now the second law, which says that for the ratio of sine I over sine R will always be a constant, and the constant is known as the refractive index of the medium. Okay, we'll zoom into examples later on. So this table gives you different types of medium, and they give you the refractive index of different medium. You do not need to memorize this. It will usually be given in exams, or you need to calculate the refractive index of the medium. So you can take a look at this. If you compare air and vacuum, air is the least optically dense material because it's gas. There's not much particles. Okay, we assume that there is very little particles blocking the light, and the speed of light, you can see over here, speed of light times 10 to the power 8. In vacuum is 3 times 10 to the power 8. So in, let me just draw one more vacuum. It will be equals to 3. Okay, and in air, there's almost very little particles blocking it. So you can see that the speed of light is almost the same. It's 2.99 times 10 to the power 8. So when you have, when you compare the refractive index of air and refractive index of vacuum, it will be very close to 1. We say that they are very similar refractive index. Okay, because refractive index is C over V, 3 times 10 to the power 8 divided by V, 2.99 times 10 to the power 8. They are almost the same. So the ratio is close to 1. But if you take a look at this entire table, the one with the highest refractive index is diamond over here. Diamond has a refractive index of 2.40. It means that the speed of light in diamond actually slows down by 2.40 times. So instead of traveling 3 times 10 to the power 8 in vacuum, once I hit diamond, I will slow down by 2.40 times. So the speed of light in diamond is 1.25. So you can see that the larger the refractive index means the slower the speed of light. Means I'm very, very, very dense. I slow down the speed of light a lot. Okay, so you can see the next example. Refractive index of water, just now you have seen already, is 1.33. It means that when light enters from vacuum or air into water, I slow down by 1.33 times. Okay, so my speed of light in water is only 2.25 times 10 to the power 8. Okay, I not slow down by 2.40. Diamond slows down a lot. Water only slows down by 1.33 times. Okay, and because the ratio is N equals to C over V, C is always bigger than V. Okay, C is always 3 times 10 to the power 8. Nothing is faster than 3 times 10 to the power 8. So this ratio will always be greater than 1. It's always a bigger number in the numerator divided by a smaller number. Big number divided by small number will always be greater than 1. And it has no units because I'm taking speed divided by speed. Meter per second divided by meters per second. The units will be cancelled out. So if you were to do any calculations and you get the refractive index is less than 1, that means your calculation is confirmed wrong. There is nothing that can have refractive index of less than 1 because there is nothing where the speed of light is faster than 3 times 10 to the power 8. Okay, then we'll take a look at the word example. Calculate the speed of light in crown glass, given that the refractive index of crown glass is 1.52. So you have learned two formulas, okay, for refractive index. One is N equals to C over V, and one is N equals to sine I over sine R. Okay, these are the two equations that you have learned. Okay, and this N is the refractive index. So now I'm interested in speed of light. So obviously I'm going to use equation number 1. So I will to write the equations, N equals to C over V. Then I will to sub in my number. So the refractive index is 1.52. Okay, you should know C is always speed of light in vacuum, 3 times 10 to the power 8 over V. V is the speed of light in that crown glass, the medium. Okay, so I need to solve for V. V will be equals to 3 times 10 to the power 8 divided by 1.52. So if you are smart enough, okay, you will just take 3 divided by 1.52 because I will keep my times 10 to the power 8 behind. I will not sub in my times 10 to the power 8. So I will be able to get 3 divided by 1.42. I'll get 1.97, and then I'll bring down my times 10 to the power 8. Okay, instead of doing this, 3 times, instead of keying in my calculator, 3 times 10 to the power 8 divided by 1.52. I'll just take 3 divided by 1.52. Okay, here, let me just erase a bit. So the correct way to be faster in your exams is just 3 divided by 1.52. Okay, next, okay, you can work on this again. I give you the speed of light in diamond is 1.24 times 10 to the power 8. What is the refractive index? Again, you are going to use the first formula, N equals to C over V. So I'm going to start in, C is 3 times 10 to the power 8 over V, which is speed of light in the diamond, 1.24 times 10 to the power 8. So I'll just take 3 divided by 1.4. Okay, just mathematically, this part, I will just take 3 divided by 1.24. I will get 2.42. Okay, and then times 10 to the power 8, divide by times 10 to the power 8. You cancel away the times 10 to the power 8. Okay, next one, checkpoint. What happens to the speed of light when it travels from air into another medium which has greater refractive index? You may pause the video to think. Let's go through. Okay, so when you have greater refractive index, it means that the larger the refractive index, it means that the slower the speed of light. So if I have a refractive index of 1.3, it means that the speed of light slows down by 1.3. But if I have a larger refractive index of 2.5, it means the speed of light slows down by 2.5 times. So the answer is actually A. The greater the refractive index, the slower the speed of light. The more, it means that the medium is more optically dense, the speed of light will be slower, and therefore it will bend more. Okay, so you can see over here, summary. The larger the refractive index, light will slow down even more because it's more optically dense, and when light slows down even more, it will bend even more. When it bends more, the angle of refraction will be smaller. Okay, let's have the practice 12.2. The formula N equals to C over V gives the refractive index N of any medium. If the second medium is also a vacuum, that means I'm going from vacuum to vacuum. Okay, so let me just draw. This is vacuum. Okay, which is 3 times 10 to the power 8. It's always C, is always 3 times 10 to the power 8. But now my second medium is not air, not water, not glass. Okay, my second medium, okay, is also a vacuum. So in vacuum, what's the speed? Is again 3 times 10 to the power 8. So if I have 3 times 10 to the power 8 over 3 times 10 to the power 8, then my value of n, the refractive index for a vacuum will always be 1. Okay, for air is also very close to 1. Second question, since light travels fastest in vacuum, n equals to COV must always be greater than 1. Okay, so this one, nothing can be greater than 3 times 10 to the power 8. So it's always a bigger number divided by smaller number. So you cannot get anything less than 1. Next one, the greater the slowdown in the speed of light, the what will be for the n, for the refractive index. You should know the refractive index is a ratio of how many times it will be slower. So the slower it is, the greater the refractive index. Okay, then you may read example 12b. When a light travels into an optically denser medium, does it bend towards or away the normal? You should know when I enter optically denser medium, okay, I will slow down. And when I slow down, I will bend towards the normal. Okay, next one. They say that glass has a refractive index of 1.5, water has a refractive index of 1.3. Higher refractive index means it's optically denser. So glass with higher refractive index means it is denser. So it will slow down more. Slow down. The speed of light will slow down by 1.5 times compared to in water. Water, the speed of light will only slow down by 1.3 times. So for the same angle of incidence, which one will have a larger angle of refraction? You should know that for larger refractive index, the more I slow down, the more I bend. So if I want to have a larger angle of refraction, I need to bend less. Okay, so to bend less, I need to have a lower refractive index. So you can see air to water, air to glass will bend more because glass is refractive index is more than water, is more optically dense, so I'll bend even more. So when I bend even more, my R will be smaller. So to bend less, I need to have the lesser refractive index, smaller refractive index of 1.3. So in summary, refraction is the bending of light when it passes from one medium to another due to a change in speed of light. When I move from optically denser to less dense, I speed up, I will bend away. And when I move into a denser medium, optically denser medium, I slow down and I bend towards. Okay, first law says that the incident ray, refracted ray, and the normal all lies in the same plane. The second law is also known as the Snell's law. It says that sine I over sine R will always be a constant. And there is another formula for refractive index, which says that refractive index is the ratio of speed of light in vacuum, 3 times 10 to the power 8, to the speed of light in another medium.